Hi, welcome, and let us see how we can solve this nonlinear differential equation by first of all reducing it to linear. You are given dy over dx, which is represented as y prime plus x sine of 2y is equal to x cos squared of y. So the first thing, on the left hand side, we are going to divide with the cos squared of y to have y prime divided by cos squared of y plus x sine 2y over cos squared of y, which is equal to x. So that is the first step. From there now, we rewrite sine 2y as follows. So this is y prime over cos squared of y plus 2x sine of y cos of y over cos squared y, which is equal to x. Now, sine 2y is the same as 2 sine y cos y. So that is how I have written it. Then at this level, here you can see one of the cos will cancel and we will have the following. Y prime over cos squared y plus 2x sine of y divided by cos of y, which is equal to x. This is equal to x. So you can name this as equation 1. Then we are going to let our z be equal to sine y over cos of y. Then we differentiate that equation in both the signs. So you can call this 2. So we differentiate this equation and we are going to get dz over dx is equal to, when we differentiate this, we are going by quotient rule, we are going to get 1 over cos squared y prime. That is actually what we are going to obtain. So you can label this equation. We label this equation 3. Then you compare equation 1, 2, and 3. So when you compare equation 3 in dz over dx is the same as y prime over cos squared of y. So, and you can see it is the value we have here. So instead of y prime over cos squared y, we are going to write it as dz. So writing that, we write that to obtain the following. So dz over dx plus 2xz, instead of what we have here, sine y cos y, we are going to substitute it with z. This is equal to x. Then at this level, we are going to get our integration factor as follows. Our integration factor will be given by exponential integral of 2x dx, which is equal to exponential x squared. You can call this equation 4. Then you call this 5. Then we are going to multiply equation 5 with the integration factor to obtain the following. So both sides exponential x squared dz over dx plus 2xz exponential x squared, which is equal to x exponential x squared. Now, the left-hand side of this equation can be written as d over dx bracket exponential x squared z, which is equal to x exponential x squared. You can multiply by dx both sides to obtain the following. Now, this is a product rule. When you differentiate this equation, you are going to get exponential x squared dz dx plus 2x z exponential x squared. So we multiply both sides by dx to be left on the left hand side. Exponential x squared multiplied by z is equal to x exponential x squared dx. Then we integrate both signs. We introduce the integral signs. Now, when you integrate and differentiate, you are going to get your function, which is exponential x squared z, which is equal to, when you integrate this part on the left hand side, the result will be half exponential x squared plus constant c. On how to integrate a question of this nature, check in my YouTube channel so that you can see how it is done. So we have we have z exponential x squared, which is equal to half exponential x squared plus constant c. But note that z was equal to, we are let our z to be equal to sine of y over cos of y. So tan y, sin y over cos of y, that is the same as cos tan y. So tan y multiplied by exponential x squared is equal to half exponential x squared plus constant c. You divide both sides by exponential x squared to be left with the tan of y is equal to half plus c exponential negative x squared. That way you can take tan inverse both sides to obtain the following. Y is equal to tan inverse of half plus c exponential x squared. We close the bracket. So that is the solution of our given differential equation. And thanks so much for taking time to study with me. For more such questions, tune on to my YouTube channel so that we may study together. Remember to subscribe also to this channel so that you don't miss a single video which I upload for us every day.